For today's videos, we're going to be talking about calculating conditional probabilities some more. And we talked about this already, the general multiplication rule. Now, the way we saw it before was that the probability of B, let's do the probability of A given B equals the probability of A intersect B over the probability of B. And this is the general multiplication rule. But you can solve for this. And so you can multiply both sides by the probability of B. And this cancels, and we get this, which is, this is the same thing just written backwards. I did the probability of A given B. But the whole point of this is that we really don't want to get into any of this. We don't want to get into the mathy stuff of this. We want to either use the Venn diagram or the tree, and we'll be in good shape. But one of the things we know is that if A and B are independent, then the probability of B given A is the probability of B. So if two events are independent, then the probability of them both occurring is the probability of A times the probability of B. And we've been doing this for a long time. This is just a formal definition of what we've already been doing. We flip a coin twice. What's your chance of getting heads both times? Well, 1/2 times 1/2 or 1/4. And so this is just a formal definition of something we've been doing all along. So, following the space shuttle disaster, the Challenger disaster, it was determined that the failure of an O-ring joint in the shuttle's booster rockets was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring would function properly 97.7% of the time. Assuming O-ring joints succeed or fail independently, what is the probability that all 6 would function properly? And so it's 0.977, right? Probability all is, but we're going to have to raise this to the 6th power because there's 6 O-rings. I think 3 on each independent rocket booster. And so when we do this, 0.977 to the 6th power is 0.8696, which is a fairly high probability, but that means the probability that 1 will fail is 1 minus 0.8696, or .1303, because this is really a 9.5, so this should be a 9.7, sorry, rounding error. Now that's not a huge chance, you know, a 13% chance, but remember what we're talking about is if you, the space shuttle, basically there's a big tank, and you have the space shuttle orbiter on the tank. And the solid rocket boosters were these 2 things on the side that really provided most of the thrust, even though there's thrust coming out the back of the space shuttle as well, to get it into space. And then these, when they got up, would fall off and fall away. And what a solid rocket booster means is that they've mixed the chemicals so that there's, they're frozen. They're not in liquid form, they're solid, which means they're really easy to handle and they're really easy to light. But once they're lit, they go and there's no option. And so if an O-ring fails, then it starts burning from the middle and the entire rocket burns out at once explosively and wipes everything out. So do you really want to take off in cold weather if there's a 13% chance that it's going to blow up? And the answer is no. And after they did this, they had only looked at the percentage of one of these, and they had underestimated it as well. A general rule of thumb for NASA is that in order for the moon mission to be successful, I remember this, is that this is the probability that parts had to work, is that 0.9995% of all things on the Apollo 11 mission had to work properly for them to make it to the moon successfully, which is why everything has a triple backup. So that's the kind of one we're looking for on those. So let's talk about that knot again. And this is the knot. If you ever see this, so let's read this problem, sorry. The first trimester screen is a non-invasive test given during the first trimester of a pregnancy. That's the first 3 months, to determine if there is a specific chromosomal abnormality in the fetus. According to a study published in the New England Journal of Medicine in November of 2005, approximately 5% of normal pregnancies will receive a positive result. And that's what's known as a false positive. We're going to be talking a lot about this because when we get in these conditional probabilities, some interesting stuff happens with false positives. So among 100 Williams with normal pregnancies, what is the probability there will be at least one false positive? Whenever you see the at least one, then this is a different type of problem. So how do we do at least one? Well, remember, the probability of the sample space is always 0, or the probability is, in any probability model, the probability is from 0 to 1. So the probability of at least 1, whenever you see this at least 1, is going to be equal 1 minus the probability of none. And hopefully that makes sense to everybody. So whenever you see the at least 1, you're going to want to do these type of problems as a 1 minus. So what's the if the probability of a false positive is 0.005, then the probability of no false positive is 0.95. But we're not giving one test, so the probability of no false positives in 200 tests is 0.95 to the 200th power. If you do that in your calculator, you get 0.00035. So hold on one second. Now, oh, I'm sorry, I made a typo. I didn't read this right. It wasn't a probability in 200, it was a probability in 100. Right, it says we're giving it to 100 women, not 200 women. So that's going to change this answer a bunch. So if we give it to 100 women, then it's 0.95 to the 100th power. Sorry about that typo. Or 0.00592. So that's the probability of no false positive tests. So the probability of at least one false positive test is 1 minus 0.00592. Or 0.994. So what's the probability that at least one of those women will get a false positive test? 99.4% chance. And so this reversing it and then reversing it again is the kind of problem that you would see Whenever you see this, at least one, know that we're going to have to reverse it and then reverse it back to get our answer. And we'll do another one of these in class so we really get the hang of it. So here's the conditional probability formula again. But remember, we don't want to mess with that. We want to either use the Venn diagram or the tree. So we had the example earlier of of people who read the USA Today, people who read both, people who read the New York Times, and people who didn't read any newspaper. Right? Remember, we did this in class. So you can look back at your notes. We're going to use that example. So what is the probability? And so let's show you the math using the formula, right? So you got to figure out, okay, what's the probability of A and B? Well, that's 0.05. It reads both papers. So the probability of A is 0.4, and then we start using the formula, and it becomes like that, 12.5. But if we don't even look at the formula, we just look at the Venn diagram, it makes so much sense. What is the probability that a randomly selected person that reads the USA Today? Well, that's all of this. So the total area that I just circled is 0.4. And what is also reads the New York Times, which is this, which is 0.05. And you'll see that that is this number right here, and that's the 0.125. And so instead of looking at this formula, we're going to have much better luck just looking at the Venn diagram and looking at the question they ask. And we're going to do another one of these in class as well, but we can break it down. But just look at the Venn diagram. Say, okay, randomly selected person that reads the USA Today. Okay, well, that's just this group. And then there's going to be some other condition, so it's just that divided by the area. And then here's another false positive test. So, right, a lot of places now you have to take a drug test to get a job. So many employers require prospective employees to take a drug test. A positive result in this test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees use drugs, and the false positive rate is 5%, and the false negative rate is 10%. So what does false positive and false negative mean? Well, a false positive means you didn't take drugs, but you tested positive for them. A false negative means that you did take drugs, but the result didn't say that you took them. And it'll make sense when we draw the tree diagram. So the question is, what percent of people who test positive for illegal drugs actually do it? And so this is an interesting thing, and the key to this is that the percentage in the population of people that are actually using drugs is very low. So let's just do this real simple, right? We got our first branch, and this is drugs. No drugs. This is not the test. This is whether or not they are actually using the drugs. And so up here, drugs is 0.04. So what is no drugs? Well, remember that each branch has to add up to 1, and so this is 0.96. Then it says, all right, so if we take drugs and we test negative, then the test was wrong, and that's what's known as the false negative. So this is going to be 0.1. So the positive, which is a correct test, is going to be 0.9. And then down here, it's also we're going to test positive or negative. Now here you didn't take drugs, so if you get a positive, that's wrong. That's the false positive, and that's 0.05. So this is 0.95. And so now we can get the values here at the end of each one of these by multiplying out the tree. So the people who took drugs and test positive for drugs is going to be 0.036. So about 3.6% of the population. 0.1 times 0.04. So 10% of the people who took drugs are going to get away with it, which is going to be about 0.4% of the population. This at the very bottom, people who take drugs and test negative is 0.912, right? Just 0.9, that's just 0.96 times 0.95. And then this last one is 0.05 times 0.96, and that gives me 0.48, or 4%. So then the question was, what percent of people who tested positive actually use illegal drugs? Well, what was the percentage of my positive tests? It was 0.048, which is the false positives, and 0.036, which are the correct positives. So the people who actually took drugs are 0.036. And so what we will see is that if we calculate that, we get an answer of 0.429. Or only 42% of the people who tested positive actually used illegal drugs. And the reason we get this result is this disparity right here, is that really only 4% of the population is taking the drugs. As the tests get more accurate, this problem gets less, or as the population who's actually using drugs gets larger, this problem goes away. But if we have either not a very accurate test and a small proportion of the population who will actually test positive for the test, then we start getting a lot of false negatives just because there aren't that many true positives to begin with. And we end up with this weird situation where less than half of the people who were telling you you can't work because you took illegal drugs actually took illegal drugs. This is why in most sporting competitions, you'll hear them say the first sample tested positive, and then they run a second sample. Because the probability of you getting a false positive is low, but the probability of someone getting a false positive is actually kind of high. So then we do a second test on that person. Now, if they fail the second test, the chances of you failing 2 tests in a row are really low, and so you're probably doing the drugs. But that's just to prevent against this weirdness of the false positives outweighing the correct positives, because so little of the population is actually taking the drugs. And we'll do another example like this in class. And here's just that same stuff written out nicely if you want to see all the numbers. You can pause that and write that down. So this is what we've learned. You can pause this and write all this down. But the key really is going to be doing the Venn diagrams and the tree diagrams, because those are the things, right? The expression in the statistics review sessions is the tree will set you free. And so that's what we're going to be working on a bunch in class next time. So I will see you then.